Hello, grade 12s, welcome back. This is the third section, chapter 3. We're going to do some problem solving, everybody's favorite. The topic is called optimization. Optimization in English language means to make something as good as it can be. In a mathematical sense, it has the same kind of idea. You've already seen these questions if you think back to grade 11 parabolas when they wanted you learning quadratic function, second degree functions. You always would find things like throw the ball in the air. What is the maximum height the ball reaches? Or the farmer has 800 meters of fence. What is the maximum area of a rectangular pen that he could create if he had to use those 800 meters? Those are samples of what we call optimization. The word maximize or minimize has come up a lot because we know that there's a connection to the derivative. And so instead of using the techniques that you used in grade 11, which really are only good for second degree functions, we're going to use calculus techniques so that any function we would be able to find when it's a maximum or in other cases when it's a minimum. And the process of doing that is called optimization. So an example of the kind of problem you could see even in calculus would be where the farmer has 800 meters of fence and he wants to create a rectangular enclosure for his cows, but of course he wants to maximize the area. So I did 3 sample rectangles using 800 meters of fence, and it's quite astonishing the difference in area. That's 17,500, that's 30,000, and this is only 3,900. So if you made a rectangle where you use 390 meters of fencing here and here, 10 on each end, that's 800 meters of fencing, relatively small area. But if you make this 300 instead of 390 on each side and 100 instead of 10, you've used 800 meters of fencing, but the area is now almost 10 times as much, 9 times as much. It's 30,000. So clearly, having 800 meters of fencing gives you many options. You want to choose the option that would give you the greatest possible area. And there are mathematical techniques that would allow you to ultimately calculate the length and the width that would guarantee that the area was as big as it could possibly be, which would be what the farmer wants. Another situation where this idea comes into play would be, for example, if a company wishes to create a new drink and they want to use a tin can in the shape of a cylinder. For them, optimal might mean that they can create the can using the least amount of tin. The less tin, the cheaper it is to make it. So they want to minimize the amount of tin used, but of course the container has to hold 330, and you could then make a tall skinny can or a shorter can. Which of these uses the least amount of material is cost effective for them? So that's the idea. I'm going to show you the mathematics now. We're going to do 2 examples, and we are going to either maximize in one case or minimize in the other. The technique is the same. So this first question says, if 2,700 square centimeters of materials is available to make a box with a square base and an open top, find the dimensions, meaning find the length, the width, and the height of such a box that gives the largest volume possible. So we are trying to maximize volume. Now, if you look at this question, it says that the base, meaning the bottom, is a square. And so that would allow me to designate the length and the width with the same variable, and I chose X. This dimension would be the height. What we want to do is create a box like this, use the 2,700 square centimeters of material, and maximize the volume. So how do you do that? Well, the technique is written here in steps, okay? When I say in these questions that the farmer has to use 800 meters of fencing to create his pen, or the drink has to hold 330 milliliters of liquid, or the box has to be made from 2,700 square centimeters of material, I am constraining you, holding you back, that you can't just make any box or any cylinder. You have to meet that condition. And so when you go to look at these questions, sometimes the language can be confusing. The idea would be, don't worry about it. You don't have to understand every word. These steps are designed so that you look at a question and you look only for one specific piece of information at a time. Once you have that piece of information, great. Then you go look for the next piece of information. And finding just one piece of information is usually much easier than trying to get a sense of the entire problem all at once. So if I want to get what's called the equation of constraint in this question, that means 2,700 square centimeters of material was used, is basically telling me surface area, because we know that square centimeters means area. And so we designate this box as having dimensions of x by x, length by width, and I'll call the height h. Remember that the top is open. That was designed in the question. So if I want to get the surface area of this entire shape, I'm going to take the area of the bottom, which is x squared, and then I'm going to take the area of all four sides, each of which is xh, and total surface area is 4xh, and that's what we call the equation of constraint, the equation that represents surface area. Step 2. Create the equation of the quantity to be maximized, or in the next question, minimized. Up here, it clearly says the words maximum volume. I'm maximizing volume. I'm going to create the equation of volume. Volume of a rectangular prism is simply length times width times height. Step 2 is accomplished. Step 3. Now what you do is you go back to the equation that you created called the equation of constraint. Notice there are two independent variables, an x and an h. It says isolate for one of those. Now, in many questions, that's totally your choice. In every question, it's your choice. But some choices are easier than others. Easiest here to isolate for h. And so you bring the x squared over to the other side, and then you throw the 4x over, transpose that, and boom, we have isolated for h. That brings us, so far, to step 4. This expression is to be substituted into the equation that we are maximizing. So that if you take the h and throw it away, you can now replace it with an expression that is equivalent to it, but uses only one variable. The real overriding strategy is to create the equation of whatever it is you're maximizing or minimizing in a single independent variable. And so these 3 steps are designed to take you towards that, right? We need the equation of what we're trying to maximize in one independent variable, and then we simplify. So this can reduce, and you get 2,700x minus x cubed over 4. Now you're going to watch me do a couple of questions, and you're going to notice that my preference when I'm doing optimization questions is to express this equation, the thing I'm maximizing, so it looks almost like a polynomial, adding and subtracting a bunch of terms. In this case, if I move up here, that's fairly easy to do because I'm going to factor that out as 1/4, and then basically I have 2,700x, and that's like having, well, that is a polynomial expression. And that's how I like my equation to look, simplified and the addition or subtraction of terms. And now I'm ready to go to step 5. Step 5 says, take the derivative of this function. I shall do so. We know that the coefficient 1/4 just gets copied. The derivative of the first term is 2,700, the second term, 3x squared. And that's the derivative. Now it says in step 6 to set it equal to 0 and solve. Remember, because whenever you're trying to find a max or a min, you always find where the derivative equals 0. And so that's what I'm going to do here. I transpose the 1/4 to the other side, which leaves me with 2,700 minus 3x squared. I'll transpose this to solve this quadratic, the second degree equation quickly. I get plus or minus 30. Remember, there's 2 solutions. But noting that x is a variable that represents a dimension, it can't be negative, you would discard the negative. And so you have the fact that the derivative equals 0 when x is 30 centimeters. Now you can verify for yourself that that would correspond to a maximum value, because you can check the signs of the derivative on each side of 30 to see if it's positive or negative. Remember, to be a maximum, we need increasing to change to decreasing. So if you substitute a number, and remember x never goes less than 0 because it's a dimension in here, like 10. Let's say we do it even right here. 2700 minus 300 is definitely positive up here. If we take a number bigger than 30, like 50, we get 2700 minus 3 times 2500, definitely negative, which means my function changes from increase to decrease, which guarantees that 30 corresponds to when volume has a local maximum. Now, if you go back to the section that we just finished, we had a little algorithm for determining what the ultimate absolute extreme value of a function is. We would test the value of that function at the endpoints, and we would test the value of that function where the derivative equals 0. And then we would choose the largest y value from those. You're really supposed to do that here, but we're going to cheat and skip that step because the endpoints aren't always obvious. It's not at all clear from here. Endpoints meaning how big am I allowed to let this box become, or how big could the dimensions be? They didn't give me that information. Long story short, we don't know enough about the endpoints, and so we're going to skip the step. We're just going to assume that if our derivative equals 0, that's the spot, and it's a fair assumption because it works. That's the spot where our function has a maximum. And so you basically solve the question here. Of course, you have to go back and read it to make sure you really have answered it. It says, what is the maximum volume? What is the maximum volume of the box? I haven't answered that question yet. I know the maximum volume occurs when x is equal to 30. If you're wondering what h would be, you could easily figure it out because we have this little formula right here. And we would get h is equal to 2700 minus 30 squared over 4 times 30. 2700 is 1800 over 120, which reduces, I think, 180 divided by 12. Perfect. A lovely 15 centimeters. So we have that the dimensions of the box are 30 by 30 by 15. Therefore, the volume, 30 by 30 by 15, works out to be the lovely 13,500 cubic centimeters, and guaranteed. Oh, sorry, guys. So I got the x. That's the value that made this function the maximum, the volume function. I figured out the h because we have this handy dandy little formula. I then used the formula to find volume of a rectangular prism is length times width times height to get 13,500, and that is the maximum volume. We're going to assume that where the derivative equals 0 is indeed the absolute extrema in any question. And that's how you solve it. So now I'm going to do these steps again with this other question to show you that these steps work every time. You've got to follow them. All right? So we're going to do one more example. Now, in this example, we have a cylindrical can, and it has to hold 1,000 cubic centimeters, which is a liter. That's my constraint. The volume of this has to be 1,000. And the objective says to find the dimensions, meaning the radius and the height of this can so that it minimizes, now look at the language, the cost of the metal to make the can. But there's nothing about money here. One has to understand that if one minimizes the amount of metal, automatically you're minimizing how much it costs. So really this could simply say amount of metal. So to solve this question, this is example number 2, I'm going to start step 1 by writing the equation of constraint. I am constrained by the 1,000 cubic centimeters, and the volume of a cylinder is pi r squared h. So that's step 1. That is my equation of constraint. You don't need this. The equation of constraint always has a numeric value on one side and variables on the other. Step 1. Step 2. Create the equation of the quantity that we're maximizing, or in this case, minimizing the amount of metal. Maybe not clear the first time, but really what that's saying, that's surface area. Minimize the amount, the surface area of the metal, the amount of metal you're using to create this cylindrical shape. And so that's the quantity I am minimizing. I want to use as little material as possible. So the equation that I'm of optimization is simply the surface area of a cylinder. We have a circle on top and one on the bottom that will have metal, so we have to include them. And this is called lateral surface area, which the formula looks like this. We will always provide you with formulas of things like surface areas and volumes, so you don't have to worry about it. That's not the problem. Okay, that won't be a problem. Now notice a key difference between the equation of constraint and the equation of what you're maximizing. This has a numeric value. The expression here of what you're maximizing or minimizing always has a letter here, like surface area, volume, cost, whatever is being maximized or minimized. It's a big difference. And our overriding objective, this is the one we're going to be using, but we can't do anything with it when it has 2 different independent variables, which is why step 3 tells you to use the equation of constraint and isolate. Now this is my equation of constraint. If I isolate for r, I'm going to have to square root it. I don't want to do that. I'm going to isolate for h by transposing the pi r squared to the other side. So that's the easiest way to isolate. It wouldn't have been wrong to do square root, it just would have been a nasty expression. So then when you go to step 4, the rule says substitute this expression into the equation that we're maximizing. In other words, take out the h and put this expression in, and we get this lovely equation, which if you look, no longer has too many different variables, it just has r's. So the task is simplify. So we leave the 2 pi r squared. This pi reduces. This r takes out one of them. This is like 2 over 1. So 2 times 1,000 is in the numerator, and in the denominator, we have an r. Now, this is a really, really, really strong, really strongly worded suggestion. When I'm doing these kinds of optimization questions, it is always best to express this function as the addition or subtraction of a lot of terms so it looks like a polynomial. The way I make that happen so that you don't have any fractional, rational expressions. So I don't want it to look like that, so I pull the r up. And then I have my equation of what I'm trying to maximize expressed as the addition of a few terms. I say it looks like a polynomial. It's not considered a polynomial expression once you have a negative exponent. But you see what I mean. If you do this, it makes the future calculations easier because the next step, number 5, says take the derivative of this function. So I'm going to write surface area prime, and I'm going to take the 2 in front and get 4 pi r. I'm going to bring the negative 1 in front and get negative 2,000 r to the negative 2. Now this is going to happen all the time. You're going to have a negative exponent. No worries. Expect it. The step says set the derivative equal to 0 and solve. So I'm going to change this, step 6, to 0. I'm numbering the steps only to show you how they correlate to these. Obviously, you don't have to number your steps. I set this to 0, and I get 4 pi r minus 2,000 r to the minus 2. So what I'm going to do now to solve this equation is take care of this negative exponent, and it's very easy. This is the other step you have to watch out for. So you prepare the function like this. It makes taking a derivative easy, and this is how you'll get rid of the negative exponent. You'll just multiply every term by r squared. If that was r to the negative 5, then you'd multiply every term by r to the positive 5. So when you multiply by 0, you get 0. When you multiply by the first term, it becomes 4 pi r cubed. And when you multiply it by this second term, r to the minus 2 times r to the positive 2 is r to the 0, which is 1, and 2,000 times 1 is 2,000. Basically, this nasty piece disappears. And then you proceed to solve this. Now, you bring the 2,000 over to the other side. Do not touch your calculators, you guys. Keep them by your side. But the only time you touch your calculator is on the last step. This is easy enough to reduce. If it wasn't easy, you would leave it. But basically, I can now say that I have solved for r. I took the cube root of the left side. Now you're allowed, and only now, to take out the calculator and just punch that out so that you get an approximate decimal, because we need the decimal value to make sense of what the dimension, the radius, would be. So what I get when I punch out the cube root is I get that r is approximately 5.4 centimeters. And I know this is centimeters because the volume was given originally as 1,000 cubic centimeters. If you read the question, basically you have the answer. Now, do you need to test if it really is a minimum? You don't have to. You probably should, but you don't have to, because they all work. We've set all these questions up. The book has created them. So wherever the derivative equals 0 is the value you're looking for. This is the number the radius of this can has to be to guarantee that we use the least amount of material. The question specifically says, find the dimensions, meaning the radius and the height. They don't say find how much tin they used, how much material. They just say find what the radius and the height is. So it makes it easy for me because I got the radius. All I got to do now is go back up and use this formula, right, to get the height. And I'll punch that out. 1,000 divided by pi times 5.4 squared. I put that in a bracket, otherwise order of operations. And I get times 10.9 centimeters. And so that's really the answer to the question. The dimensions are r equals 5.4 centimeters, h equals 10.9 centimeters. There's no real way to truly check if you're correct or not. The only thing is, if you're really worried, you could do that first derivative to see if it changes from decrease to increase, but it'll work. It'll work. And that's how you do it. That's the answer to number 2. So we're going to give you some questions for homework, and you're going to follow these 6 steps. That's going to be posted on the site. And you'll practice it and you'll let us know. And then the rest of this section has to do with other kinds of questions. So we're going to break them into categories. But that's for the next class. Happy work.